Good morning, or at least it is here. What I'd like to do at this point is sort of do an overview of the modern computer and talk a little bit about the history of it and things like that. So it's always easy or easier if we have some sort of script to work off of. And in this case, as with most cases, we're going to use Wikipedia because it's amazing. And it happens to be free, which is always nice. So, sorry, I'm glancing at the homepage. What we're going to do is just go here and just type in computer. We're going to get a huge page with all kinds of different things, and we'll sort of scroll through it and talk about some of the major sections and things like that. In later videos, we'll talk more about how instructions are processed by a computer and more specific things like that, but just so we have some kind of historical context to work from, which I think is important, just on a personal level, but also because I think that there's a lot of contributions, and ignorance has a bad rap, but I mean, there's nothing wrong with being ignorant about things. I'm ignorant about particle physics, but it doesn't mean I'm an idiot. So I think that there's a lot of general ignorance about all the work and some of the individuals involved in making computers what they are today, and whether it's your smartphone or your laptop or your desktop, or maybe you manage a couple servers or hundreds of servers, whatever the case may be, it all sort of started from the same point. So we're just going to sort of go through this a little bit, and in a general sense, the article starts off fairly generic and then delves into, it has some it's like linear, I guess, natural progression, I think is what I was looking to say. So we'll just jump right in here. And basically, a computer is a general purpose device that can be programmed to carry out a set of arithmetic or logical operations automatically. Since a sequence of operations can be readily changed, the computer can solve more than one kind of problem. Conventionally, a computer consists of at least one processing element, typically your CPU, and some form of a memory. The processing element carries out arithmetic and logic operations, and a sequencing and control unit can change the order of operations in response to stored information. As we get into things, like part of the series will definitely involve the same sort of content that my previous two attempts did, namely cheat engine and manipulating instructions in games and things like that. So we'll definitely get into this more as we get into that part of the series, but we're not going to focus too much on that right now. Peripheral devices allow information to be retrieved from an external source and the result of operations saved and retrieved. So peripheral devices is just a generic way. Examples would be your keyboard, your mouse, your monitor is another fairly obvious one. Mechanical analog computers started appearing in the 1st century and were later used in medieval era for astronomical calculations. We're not going to focus on that kind of stuff. I mean, the abacus being the most poignant example, I think. But we'll probably start off, as far as like this analysis or this sort of historical reading, we'll definitely start focusing on like World War II, maybe pre-World War II, so like the vacuum tube era. In World War II, mechanical analog computers were used for specialized military applications. Most people are familiar with the breaking of Enigma and things like that. That had a huge impact on how computers were used, designed, and certainly the amount of time, energy, and funding that was poured into just computing technology in general was unparalleled, and perhaps has been unparalleled since. And definitely, I mean, it's not so much you could have really great ideas and you could revolutionize, parts of industries and technology, but if you don't have the time, the money, or people to help move your idea into a practical application, then you're probably not going to do that much good, or have that much of an impact, sad to say. During this time, World War II, the first electronic digital computers were developed. Originally, they were the size of a large room, consuming as much power as several hundred modern personal computers. if you went to college in the 60s or the 70s, you're familiar with punch cards, and that's kind of the context of that statement. Modern computers are based on integrated circuits, or modern computers based on integrated circuits are millions to billions times more capable than the early machines and occupy only a fraction of the space. Simple computers are small enough to fit into mobile devices. Mobile computers can be powered by small batteries, so on and so forth. Personal computers in their various forms are icons of the information age and are what most people consider as computers. However, the embedded computers found in many devices, such as your smartphones, are the most numerous. This is very true. So we can go down and read about the etymology and the history, and we're definitely going to do that, but we are going to start right here. So we scroll up a little bit. This kind of stuff, the previous sections detail, the abacus and the Charles Babbage and stuff like that, all of which are extremely important, and certainly Charles Babbage. It's just I don't want to get too far off track, but so I'd like to start just here, but obviously if on your own time, if you'd like to read it, you certainly can do that. The digital computer age begins. The principle of the modern computer was first described by mathematician and pioneering computer scientist Alan Turing. If you don't know who Alan Turing is, or you have an interest in this kind of stuff, I would definitely suggest reading through his article. And I believe there's a movie that just came out. Is it like Differential or something like that? That's kind of based on his life. And for the amount of contributions and things that he made, it's really kind of sad how he was sort of thrown to the side. And it's, like I say, it's a Greek tragedy, but I guess it might be a Greek tragedy, but it's depressing, I guess is what I would say. He had a rough ride of it all, I guess. But continuing on, Turing reformulated Kurt Gödel's 1931 results on the limits of proof and computation, replacing Gödel's universal arithmetic-based formal language with the formal and simple hypothetical devices that became known as Turing machines. And again, if you'd like to, Turing machines are a metric, I guess is maybe the best way to say it, about how you can describe the capabilities of certain computing devices. All modern computers, certainly every one that I've ever seen, are Turing complete, is what it's known as. So if you have an interest in that stuff, definitely check out that page as well. He proved that some such machine would be capable of performing any conceivable mathematical computation if it were representable as an algorithm. He went on to prove that there was no solution to the something problem. I'm not going to butcher that word. By first showing that the halting problem for Turing machines is undecidable. In general, it is not possible to decide algorithmically whether a given Turing machine will ever halt. And again, there's more details on that in probably the halting problem as well as the Turing Machines article. He also introduced the notion of a universal machine, now known as the universal Turing machine, with the idea that such a machine could perform the tasks of any other machine, or in other words, it is probably capable of computing anything that is computable by executing a program stored on tape, allowing the machine to be programmable. The implications of that are enormous, which we'll start to get into as we keep going. Von Neumann acknowledged that the central concept of the modern computer was due to this paper. Turing machines are to this day a central object of study in theory of computation. Except for the limitations imposed by their finite memory stores, modern computers are said to be Turing complete, which is to say they have algorithm execution capability equivalent to a universal Turing machine. And this part here, except for the limitations imposed by their finite memory stores, is just what they're essentially indicating there. And maybe it's obvious to you if you have a background on this stuff, but in the event that you don't, they're essentially just saying that there's not an unlimited amount of memory in your computer, whether it's the RAM or it's like a virtual storage or virtual memory rather, or your hard drive. All computers have some limited amount of storage, and that limits to some extent the amount of information that they can process at once. You almost never practically run into that limit. Certainly, you might if you do work on supercomputers and are trying to simulate nuclear explosions, but for most practical, modern consumer grade things, you almost never run into that problem. The first electromechanical computers. By 1938, the United States Navy had developed an electromechanical analog computer small enough to use aboard a submarine. A common theme through the beginning of all this stuff is basically that the military was the first, not just the United States military, but certainly them, but militaries in general were the first to say, hey, computers can do automated things, it reduces the amount of error, and they can do it a lot faster than humans. That makes my war machines a lot more effective. So if you could install that kind of stuff in a tank and you didn't have to calculate ballistic trajectories by hand, and you could just offload that to a computer, you'd have a much more effective tank, which is probably exactly what they do now, nowadays. This computer on the sub was the torpedo data computer, which used trigonometry to solve the problem of firing a torpedo from a boat to a moving target. During World War II, similar devices were developed in other countries as well. We pretty much just talked about that. Early digital computers were electromechanical. Electric switches drove mechanical relays to perform the calculation. These devices had a low operating speed and were eventually superseded by much faster all-electric computers, originally using vacuum tubes. The Z2 was one of the earliest examples of an electromechanical relay. This whole sort of stuff about electromechanical relays and vacuum tubes I find it historically very interesting. Just if you ever pull up an image, we'll just do that real quick. Go to Google. Let's search Google Images or something. We'll do like a vacuum tube relay image or vacuum tube. Yep. So I don't know. It's kind of, that's what a vacuum tube looks like, and the early computers were built out of lots of these. Probably Z1 and Conrad. Yeah. So here's an example of a electromechanical vacuum tube, or I'm sorry, not electromechanical, but a vacuum tube computer. It's a lot different. Imagine having that on your desk or next to your desk instead of what you have now. In 1941, Zeus followed his earlier machine. I'm pronouncing it Zeus, but anyway, followed up with the Z3, the world's first working electromechanical programmable fully automatic digital computer. It was built with 2,000 relays, implementing a 22-bit word length that operated at a clock frequency of about 5 to 10 hertz. If you have a Casio watch, it probably is 50,000 times faster than that. Program code and data were stored on punched film. It is quite similar to modern machines in some respects, pioneering numerous advances such as floating point numbers. Floating point numbers are essentially just decimal numbers, is what most people are familiar with. So 1.2345 or pi is a good example of that. And as definitely we'll touch on floating point numbers as we go through some of this other stuff. Replacement of the hard-to-implement decimal system used in Charles Babbage's earlier design by the simpler binary system meant that Zeus's machines were easier to build and potentially more reliable, given the technologies at the time. The Z3 was probably Turing complete. The introduction of digital electronic programmable computers with vacuum tubes. Purely electronic circuit elements soon replaced their mechanical and electromechanical equivalents. At the same time that digital calculation replaced analog, the engineer Tommy Flowers, working at the Post Office Research Station in London, began to explore the possible use of electronics for telephone exchange. Experimental equipment that he built in 1934 went into operation 5 years later, converting a portion of the telephone exchange network into an electronic data processing system using thousands of vacuum tubes. You'll probably skip through some of this stuff. Again, obviously, it's right on the screen, so you can either pause it and read it, or you can just go read the article if you want to get the full experience. During World War II, the British at Bletchley Park achieved a number of successes at breaking encrypted German military communications. The German encryption machine, Enigma, was first attacked with the help of electromechanical bombes. To crack the more sophisticated German machine, or encryption method, used for high-level Army communications, Max Newman and his colleagues commissioned Flowers to build the Colossus. Spent 11 months from February 1943 designing and building it. After a functional test, it was shipped to Bletchley Park, so on and so forth. Colossus was the world's first electronic digital programmable computer. used a large number of valves that had paper tape input and was capable of being configured to perform a variety of Boolean logical operations on its data, but it was not Turing complete. And Boolean logic is something that we'll definitely deal with quite a bit as well. Colossus Mark I contained 1,500 tubes, but Mark II with 2,400 valves was both 5 times faster and simpler to operate than Mark I, greatly speeding up the decoding process. The US-built ENIAC, was the first electronic programmable computer built in the US. Although ENIAC was similar to Colossus, it was much faster and more flexible. It was Turing complete and could compute any problem that would fit into its memory. That's sort of the demarcation point that modern computers all come from. If you can fit it in the memory, it'll solve the problem, assuming that you can instruct it how to solve that problem. But that's more of a limitation of humans than it is the computer. Like the Colossus, a program on the ENIAC was defined by the states of its patch cables and switches, a far cry from the stored program electronic machines that came later. We'll definitely get to that. Once a program was written, it had to be mechanically set into the machine with manual resetting of plugs and switches. So if you can imagine, if you wanted the computer to do something, you'd have to sit down and rewire a whole bunch of boards and stuff, and not very efficient, but got the job done. It combined the high speed of electronics with the ability to be programmed for many complex problems. It could add or subtract 5,000 times a second, 1,000 times faster than any other machine. Also had modules to multiply, divide, and square root. High-speed memory was limited to 20 words, about 80 bytes. The machine was huge, weighing 30 tons, using 200 kilowatts of electric power, and contained over 18,000 vacuum tubes. That is ridiculous, frankly. So if you talk to people who, again, probably went to college in the 70s or even the 60s, they'll tell stories about huge wall-mounted computers that were bigger than the house. And so they have this nice picture, and that hardly looks like a computer at all, frankly. But it did its job. Early computing machines had fixed programs, and changing its function required the rewiring and restructuring of the machine. With the proposal of the stored program computer, this changed. A stored program computer includes by design an instruction set and can store in memory a set of instructions or a program that details the computation. This is what all modern programs use, all modern computers use, and is something that we'll definitely get into, whether we're looking at like a programming language or like a cheat engine kind of thing. This, again, huge milestone. The theoretical basis for the stored program computer was laid by Alan Turing in 1936. In 1945, Turing joined the National Physical Laboratory and began work on developing an electronic stored program digital computer. His 1945 report proposed electronic calculator was the first specification for such a device. Von Neumann at the University of Pennsylvania also circulated his first draft of a report on the EDVAC in 1945. Kind of zip through take a look at this. The Manchester Small-Scale Experimental Machine was the world's first stored program computer. It was built at the Victoria University and ran its first program on June 21st. It was designed as a test bed for the Williams tube, the first random access digital storage device. Although the computer was considered small and primitive, it was the first working machine to contain all of the elements essential to fit a modern electronic computer, or essential to a modern electronic computer. As soon as the SSEM had demonstrated the feasibility, a project was initiated at the university to develop it into a more usable computer, the Manchester Mark I. Some of you may be familiar with that. We're going to skip ahead here. Transistors replaced vacuum tubes, another critical milestone. The bipolar transistor was invented in 1947. From 1955 onwards, transistors replaced vacuum tubes in computer design, giving rise to the second generation of computers. Compared to vacuum tubes, transistors have many advantages. They're smaller, use less power, so give off less heat, which is kind of a well-known limitation on circuit board design and hardware in general, and is a huge concern when if you're thinking in you step back a bit and you're thinking about modern processor design. It's really hard to shrink this stuff right now because there's so much packed on there that the heat, it just radiates so much heat that you have to find a way to cool it off, which takes more power, and it's just kind of this It's a really hard problem to solve. So the move is more towards like parallelism and different multi-cores and stuff like that. That's kind of where that like multi-core movement came from. I mean, it had been around for a while, but just as an interesting A side, I mean, there were practical things that started encouraging companies to slap multiple cores on, or to go into a parallel design as opposed to just having one a uniprocessor that just making it faster and faster and faster. And again, that's sort of the central driving force is just that. Moving on, transistors are much more reliable than vacuum tubes, had a longer indefinite service life. Transistorized computers could contain tens of thousands of binary logic circuits in a relatively compact space. Let's see, they're first in the world. First transistorized computer and the first in the world was operational in 53, and a second version was completed in 55. However, the machine did make use of valves to generate its 125 kilohertz clock waveforms and in the circuitry to read and write on its magnetic drum memory, so it was not completely transistorized. That distinction goes to the Harwell Cadet in 55. The next great advance in computing power came with the advent of the integrated circuit. The idea of the integrated circuit was first conceived by a radar scientist working for the Royal Radar Establishment, quite the name, of the Ministry of Defense, Jeffrey Dummer. Dummer presented the first, is it Dummer? Dummer presented the first public description of an integrated circuit at the Symposium on Progress and Quality Electronic Components in DC in 52. The first practical integrated circuits were invented at Texas Instruments and at Fairchild Semiconductor. Kilby recorded his initial ideas concerning the integrated circuit in 58, successfully demonstrating the first working integrated example on 58. In his patent application in 59, he described his device as a body of semiconductor material. I'm going to kind of jump around here a little bit. This new development, integrated circuits, heralded an explosion in the commercial and personal use of computers and led to the invention of the microprocessor. While the subject of exactly which device was the first microprocessor is contentious, partly due to lack of agreement on the exact definition of the term microprocessor, it's largely undisputed that the first single-chip microprocessor was the Intel 4004, designed and realized by Ted Hoff, Federico Fagin, and Stanley Mazur. Mobile computers become dominant. This skips ahead about, I'm going to say, what's the last date in here? 59. And this one talks about mobile computers being dominant 50 years later. So there's quite a gap there. And that's not to say that there's been no progress, and anyone who says that is being disingenuous. But integrated circuits and stored program architecture form the basis for all modern computers over the last 50 years. And there's been various changes and tweaks and whatnot, or at least as I understand it, they formed the basis for over the last 50 years. There's been changes and tweaks in the way that those things run, and there's definitely special purpose computers that work on a different sort of work in a different paradigm and are designed not according to those standards or use different forms of technology. Most notably, they won't use a stored program architecture. They'll use something else. But we sort of zip through it. But if you read through and you get to this point down here, this is pretty much where all modern computing began. Or at least as we see it now. In 50 years, modern computing will probably be something entirely different. But we'll just keep reading here a little bit. Talk about program/applications. The defining feature of modern computers, which distinguishes them from all other machines, is that they can be programmed. That is to say that some type of instructions, the program, can be given to the computer and it will process them. Modern computers based on the von Neumann architecture often have machine code in the form of an imperative programming language. I'm hesitant to open up the von Neumann architecture article because it gets really pedantic, starts getting into like extremely low-level hardware stuff. So instead what we'll say is we'll just acknowledge that this article exists and you can definitely read it for a more complete background. As far as an imperative programming language, we will get to that at some point because we'll fool around with some programming languages. In practical terms, a computer program may be just a few instructions or extend to many millions of instructions, as do the programs for Microsoft Office or Google Chrome, for example. A typical modern computer can execute billions of instructions per second, also colloquially known as gigaflops. Rarely make a mistake over many years of operation. Large computer programs consisting of millions of lines take years to write, and due to the complexity of the task, almost certainly contain errors. I think a subtle distinction or a subtle note that this article is trying to make in those last two sentences, or the last sentence and a half, is that a problem with the computer that's not hardware based is almost never going to be the result of it not adding or doing operations correctly. It's always going to be the result of the human or the developer or whatever, the user, if you want to be more generic, telling the computer to do something in the wrong way. So, I mean, even if we just bring up a calculator and we want to I'm just going to use something stupid, but like, what's 9 times 8? So, computer says it's 72. You could hit 9 times 8 500 million times and it's never going to come back with a different answer. However, if we are just not paying attention, or we've had a long day, or drank 10 cups of coffee and can't see straight, you might actually click 9 times 9, hit equals, and you're like, well, no, that's, and maybe you just don't know how to do multiplication, or whatever the case may be. Maybe you use the result of that calculation in a larger calculation, and then that calculation's wrong, and you're like, well, what the hell? You go back and you find out that you had actually just done 9 times 9 instead of 9 times 8. That's kind of what they're getting at here, is that it's the user who's going to be the cause of pretty much anything that the computer does wrong. The computer is never wrong, and the user is rarely right, I guess. Stored program architecture. This section applies to most common RAM machine-based computers, which is pretty much all modern desktops, laptops, things like that. In most cases, computer instructions are simple. Add one number to another, move some data from one location to another, send a message to some external device, etc. These instructions are read from the computer's memory, are generally carried out or executed in the order they were given. So what they're saying is that usually it's sequential execution. So it's, let me do operation 1, I'll do operation 2, I'll do operation 3, 4, ad infinitum until I either get a new set of instructions to perform, or until I run out of stuff to do, in which case I'll just sit there and count sheep. However, there are usually specialized instructions to tell the computer to jump ahead or backwards to some other place in the program and to carry on executing from there. This basically forms the idea of what they call control flow, or flow of control, I guess is, some people just say it differently, but as we kind of work through this, and certainly when we screw around and do some programming, and definitely when we look at like cheat engine type stuff, we'll absolutely deal with this pretty much on a constant basis. These kinds of instructions are called jump instructions or branches. And jump instructions may be made to happen conditionally, so that different sequences of instructions may be used depending on the result of some previous calculation or some external event. Many computers also directly support subroutines by providing a type of jump that remembers the location that it jumped from, and another instruction to return to the instruction following that jump. Some of that's, the wording there seems a little like or maybe not as clear as it could be, but suffice to say that when I first learned how to program and I learned about computers, as soon as I understood this and I realized that I could make the computer conditionally do stuff, I immediately thought, well, I could write any program in the world, any idea. Because if you can conditionally check for, if you can check for conditions, then even the most craziest problems in the world that have millions of permutations, if you had the time and the motivation to write all of those millions of conditionals, in my head, I was like, well, theoretically, you could write anything. Turns out that it's not that practical, and I suppose that from an absolute perspective that still may be true, but that is generally not the practice that software development or program application development takes. But I just remember that it was a huge thing for me when I realized that that the execution path that the computer's taking could be adjusted based on the value of numbers or data or basically things like that. Program execution might be likened to reading a book. While a person will normally read each word and line in sequence, they may at times jump back to an earlier place in the text or skip sections that are not of interest. Similarly, a computer may sometimes go back and repeat the instructions in some section of the program over and over again until some internal condition is met. This is called the flow of control, or control flow as I call it, within the program, and it is what allows the computer to perform tasks repeatedly without human intervention. Comparatively, a person may use a pocket calculator, or a person using a calculator can perform basic operations such as adding two numbers with just a few button presses. To add together all the numbers from 1 to 1,000 would take thousands of presses, a lot of time, and you'd probably make a mistake. On the other hand, a computer can be programmed to do this with just a few simple instructions. For example, here's some basic pseudocode that whoever put this in the article hoped is relatively approachable to a general audience. It is pretty approachable and is not far off the mark. So instead of having a queue, I don't know why you'd want to add 1 to 1,000, but in the event that you did, you could pay someone to sit there for probably 3 days, and then you'd have to pay someone to double check them, and then you'd probably wind up double checking it yourself, assuming that you needed the result of that calculation in some important application. Whereas you could just have the computer do it with probably, what's that, like 4 or 7 lines of code, or pseudocode, but it's more or less the point stands that if we sort of like take this sort of analogy and then we look back towards like when we were talking about how the military funded it and stuff, like you could see why the military would look at this sort of scenario and say, yeah, I want that. And certainly there's consumer applications as well, but moving on. Once told to run this program, the computer will perform the repetitive addition task without human intervention. It will almost never make a mistake, and a modern PC can complete the task in about a millionth of a second. That's pretty desirable is what I would say. So that's a relatively good example. And we'll move on and talk a little bit about machine code. In most computers, individual instructions are stored as machine code. This is kind of like the lowest level stuff that people, what you see in movies and they talk about in pop culture and stuff like that, where like, I program in ones and zeros. No, you don't. Or maybe there's like, half of 1% of people in the world who do because they work with like really low level hardware and stuff. But, and they did back in like the 50s and 60s and stuff. But, there's no reason to deal with it. And machine code is more or less what instructs the computer to, like, its native language, if you will. I don't want to talk too much about machine code. I mean, we're going to read through this, but obviously there's a link here, and you can certainly go there and read about machine code in depth. In most computers, individual instructions are stored as machine code, with each instruction being given a unique number, or its opcode. The command to add two numbers together would have one opcode. The command to multiply them would have a different opcode, and so on. The simplest computers are able to perform any of a handful of different instructions. More complex computers have several hundred to choose from, each with a unique numerical code. Since the computer's memory is able to store numbers, it can also store the instruction codes. This leads to the important fact that entire programs, which are essentially just lists of those opcodes, can be represented as lists of numbers and can themselves be manipulated inside the computer in the same way as numeric data. This idea of storing programs in the computer's memory alongside the data they operate on is the crux of the von Neumann or stored program architecture. In some cases, a computer might store some or all of its program in memory that is kept might store some or all of its program in memory that is kept separate from the data it operates on. This is called the Harvard architecture after the Mark I. Modern von Neumann computers display some traits of the Harvard architecture in their designs, such as in CPU caches. If you want to read about the Harvard architecture, you can certainly check out that article. While it is possible to write programs as long lists of numbers, machine language, machine code, and while this technique was used with many early computers, it's extremely tedious, extremely error-prone, especially for complicated programs. Instead, what's usually done is each basic instruction can be given a short name that is indicative of its function and easy to remember. This is essentially assembly code, but mnemonics such as add, sub, mult, or jump. And assembly language is what you see when in the last series or one of the previous series when we were fooling around with Cheat Engine, we'd open up and see all this like add, sub, conditional jump stuff. That's kind of like the instructions of the game that we were hacking on, more or less. as mnemonic of the actual machine code or the opcodes that were being used to tell the processor what to do. And by manipulating that, we were able to basically just eliminate parts of the game that we didn't like, such as taking damage or movement points or something like that. These mnemonics are collectively known as a computer's assembly language. Converting programs written in assembly into something the computer can actually understand, or converting it into machine code, is usually done by a program called an assembler. We'll probably, again, as far as cheat engine goes, we'll fool around with this a little bit, but what we're probably not going to do is go download like an actual assembler and write some x86 assembly or something like that. I'm not sure that there's value in that. I mean, maybe if like people want to do that, that's fine. I did a little bit of that in college and it was fun. I did a little bit of that on my own time before I went to college and it was fun. But the practical applications, unless you get paid to do that and you're doing like hand optimizing code or like really low level embedded stuff, there's not a whole lot of, I didn't find a whole lot of tangible benefit. Rarely do I use it in my current job or in any of my previous jobs, so it's just not something that I spend a lot of time on. But again, we can certainly do it if people want. From a more generic or general perspective, programming languages in general provide ways of specifying programs for computers to run. Unlike natural languages, English, Chinese, Spanish, so on and so forth, programming languages are designed to permit no ambiguity and to be concise. They are purely written languages and are often difficult to read aloud. They are generally either translated into machine code by a compiler, known as compiled languages, or an assembler before being run, or translated directly at runtime by an interpreter, known as interpreted languages, or scripting languages, more often than not. Sometimes programs are executed by a hybrid method of these two techniques. We'll definitely get into this more, specifically in this. We'll probably deal with like Python. We made it a point to install it in the previous video, so. Low-level languages, programming languages in general are kind of like broken up into what are considered low-level and high-level languages, and the distinction there is that a low-level language is closer to the machine code or assembler, and high-level languages are more farther removed from it and generally give you less of an ability to directly interact with the hardware. But productivity goes up because if you're writing a web browser, there's no need for you to talk to the hardware directly, or not usually anyway. So that's kind of the distinction between low level, high level, and there's no, I find that while there may be some academic definition of where that line between low level and high level is, in practice everyone sort of draws that line in a different place, and it's also a relative thing, which is to say that 30 years ago, 40 years ago, C would be considered a high-level language, but because before C, people wrote in, Fortran, Algol, assembler, stuff like that. All that kind of stuff is really common, and everyone was kind of like low, like just sitting on top of the hardware, removed by like one, maybe two levels. So now in things like really high-level languages like Java and Python and stuff like that didn't exist. So fast forward to modern day. Now you have really high-level languages, and Google Go and stuff like that, where C is now probably considered a low-level language. If you ask 8 out of 10 application software developers nowadays who just sit around and bang out application code like word processor stuff, they would probably consider C to be a low-level language. But again, it's important, and that's a distinction that we will use, or that's a sort of a nomenclature that we'll use a lot. And we'll say, well, this is low level, this is high level, and that when we draw that line, you should definitely be thinking to yourself, okay, this is low level, so we're close to the hardware and things are weird or going to be complicated. And if it's higher level, then generally higher level things are just more approachable to humans and easier to teach, easier to understand. So again, it's not just limited to programming languages. We'll use that sort of vernacular in many different contexts. But moving on, low-level languages, machine languages, and assembly languages that represent them tend to be unique to a particular type of computer. For instance, an ARM architecture computer, such as what you'd find in a PDA, cannot understand the machine language of an Intel Pentium or an AMD Athlon that might be in a PC or desktop. The whole point of having compilers and things like that is, in scripting languages, interpreted languages, is to remove the concern of what platform am I running on. So the compiler, you write some code in C or you write some code in Python, and then you run it on your machine, so you know it runs on your computer. If you forklifted that over to an entirely different architecture, if you compiled it with the C compiler on that system or the Python interpreter on that system, or interpreted it with the Python interpreter on that system, it would run. So a huge movement when programming languages first came around was to let's make this stuff hardware independent so we can focus on solving the problems and writing the applications and making computers generally more accessible, usable, and fun, as opposed to I have to rewrite everything because I just moved to a different platform. And commercial companies obviously love this because it allowed them to write their application more or less once and then just sell it to everybody, thus increasing the amount of like market share / penetration that they could get. Higher level languages, considerably easier than in machine language. Writing long programs in assembly is difficult and error prone. That's an understatement, but suffice to say it's very true. Most practical programs are written in more abstract, high-level programming languages that are able to express the needs of the programmer more conveniently and thus help reduce programmer error. High-level languages are usually compiled into machine language or sometimes into assembly and then into machine language using another program called a compiler. High-level languages are less related to the workings of the target computer than assembly and are more related to the language and the structure of the problem to be solved by the program. It's therefore often possible to use different compilers to translate the same high-level language program into the machine language on many different types of computer. This is part of the means by which software like video games may be made available for different computer architectures, such as personal computers and various video game consoles. So, let's say two things about what we just read. The first one is, if you want to understand what a compiler is, click on that article for a compiler, but just unless you have a background on that stuff, expect to have your mind completely melt. It's an extremely complicated topic, and the software or the people that write compilers and things like that, it's just incredibly complicated. And if you're interested in that kind of stuff, definitely read this article and look up, I want to say it's called The Dragon Book. I think it's called The Dragon Book. It's kind of like the colloquial term for it. It's like compiler design. I had this book in college. Here we go. This is kind of like a staple, if you will, when it comes to compilers and designing them and lexical analysis and things like that. The Dragon Book. So definitely check that out if you have an interest in that stuff. But again, it is crazy. It gets really complicated, especially the lexical analysis and the parsers and stuff like that. And the second thing is the means by which software like video games may be made available for different computer architectures, such as personal computers and various video game consoles. Microsoft released something kind of like their Common Language Runtime, I think it's called, the CLR, and basically their .NET framework kind of like sits on that, and that framework takes the idea of this and basically says write your program once, and as long as you have this .NET framework installed, you can run it on any machine. And a partner project to that is what's called Mono, which is kind of like a cross-platform implementation of .NET more or less, and we'll deal with this in much more detail and kind of dive in and take a closer look at it. But I occasionally, I occasionally talk to people who are like, well, this is BS, why is Microsoft this, why is Microsoft that? Just be happy that all companies, especially Microsoft, are getting on board with this idea, and they're writing these kind of frameworks, and they're providing some kind of open licensing for them so that things like Mono can exist. And this is a huge thing. If we ever get to the point to where you can write a program once and it'll run on a Windows, Linux, and Mac machine, is that going to radically change the universe? No, but it's going to allow people to, like we were talking before, it's going to allow them to focus on the problem they're trying to solve, as opposed to worrying about vendor lock-in and other BS concerns. In this specific arena, I'm biased because I think that that's a great thing. That kind of stuff should be open, free, and anyone should be able to use it. And specifically when it comes to video games, people are starting to build a lot on the Unity engine, and that's because Unity is built on top of this like .NET Mono framework, and you can just like build it once, and then you can sell it to people who run Linux, and you can sell it to people who run Windows. and that's a great thing. But editorial over. Program design. Program design of small programs is simple and involves the analysis of the problem, collection of inputs, use of the programming constructs within languages, devising or using established procedures and algorithms, providing data for output devices, and solutions to the problem as applicable. It's a ridiculously long sentence. As problems become larger and more complex, subprograms, modules, documentation, new paradigms such as object-oriented programming are encountered. Suffice to say that the larger, basically we're just going to start editorializing here. The larger the program is, the harder it is to make. That's essentially what they're saying. We'll read this just because it's funny, and then we'll probably split this up. And we talked to, well, we'll just read this first. Errors in computer programs are called bugs. They may be benign and not affect the usefulness of the program, or have only subtle effects. In some cases, they may cause the program or the entire system to hang, becoming unresponsive to inputs such as mouse clicks or keystrokes, or to completely crash. If you've ever seen a blue screen, if you're using Windows, if you've ever had a kernel panic when you're using like OS X or Linux, that's essentially what's going on. There's some kind of assumption or bad memory access or something that's just locking up the whole system. Otherwise, benign bugs may be harnessed for malicious intent, exploits, codes, things like that. What I really wanted to read was Admiral Grace Hopper, an American computer scientist and developer of the first compiler, is credited for having first used the term bugs in computing after a dead moth was found shorting a relay in the Harvard Mark II computer. And it's kind of funny. I think it's funny. First actual case of bug being found. Here's a moth. I don't know. So that's why we call them computer bugs, apparently. So basically, let's sort of just recap here what we sort of reviewed, like how we got from the initial sort of like vacuum tube mechanical computers down to basically, there's this guy, Alan Turing, and he had all these great ideas. One of his really great ideas, along with other people, was let's store the program in the memory as well, and the instructions right next to it. And turned out to be a massively powerful idea. And on top of that, the hardware slowly caught up. We had transistors, and then we had integrated circuits. And when you put those two ideas together, you eventually got microprocessors and got what we define as modern computers. We reviewed kind of what programs are a little bit, and even took a look at like instruction sets and talked about what machine code was. We'll delve more into what machine code / assembly is. Again, probably not going to download an assembler and mess with it, but when we start messing around with cheat engine and things like that, and in other areas as well, we will have to come back and just kind of touch on this from time to time. And we'll develop, in the event that it's not clear now, we'll certainly develop a larger or a better context within how we can actually look at what machine code is. It'll become much clearer. Then there's programming languages, there's low level, there's high level, things like that. And we talked about the distinction between the two. Read a little bit about program design, which is basically stuff's really hard unless you're writing a simple, small program. And even then it can be really hard. Kind of depends on what you're trying to accomplish. And then we looked at the first computer bug, which was an actual bug stuck in a computer. So we're going to kill this here, or stop this here, and then we'll come back and start looking at more of like what the hardware components are, and start going through like memory and stuff like that, and how the hardware sort of allows us to do the things that we're familiar with, such as graphical displays and things like that.